So in this video, we'll be looking at what's the Taylor series, the Taylor's theorem and the remainder term, and we'll be estimating the error in a Taylor polynomial approximation of a function. So let's begin. The Taylor series. What is the Taylor series? Before we get to what's the Taylor series, we need to actually connect some concepts that we've looked at already. And the main concept I'm, of course, hinting towards is power series. The power series we mentioned is basically used for one of the major applications is to represent functions. So any function is expressible in the form of a power series. This is a very important application of power series. And what we mean by this is if we start by making an assumption that what we mean by a function represented as a power series, which is of course has some radius of convergence r, which is positive. So let's say that f of x is equal to the general power series k equals 0 to infinity bk into x minus c to the power k. So here we have a power series and a function that represents is supposedly a power series that represents a function. Now, in order for this, we have to find this bk. What it essentially means is here's a general power series. How could we find the bk and to basically find the power series? The c can be fixed. It's easy. We can just say fix a c, a constant. It's a parameter. But the bk are what make the power series flexible. So in order to find these bk, what we can do is we can look at what are the derivatives. What is the derivative of the power series? For instance, if we look at f dash of x, well, f dash of x, and by the way, here I'm just going to show you the term by term just for reference sake. So it's b1 into x minus c plus b2 into x minus c squared plus b3 into x minus c cubed, and so on. Okay, so f dash x would be the derivative, as we have done in the previous video. The bk is a constant, so nothing happens to that. The k comes down, the power x minus c to the k minus 1. Okay, and if we look at it in term by term form, the b0, the derivative of b0, it's gone. Okay, so what's left is just b1. So we get b1 plus 2b2 into x minus c plus 3b3 into x minus c squared plus, and so on, let's say. Okay, so now, okay, so f of c would mean that this term, and this term, and this term, and all the terms onwards, which are all powers of x minus c, would in fact go to 0. So the only non-zero term remaining would be b0, right? So, fair enough. In the same way, if we try now to calculate what happens at f dash of c, well, let's have a look at that. So in this case now, this term, and all terms onwards will become 0. The only non-zero term remaining would be, of course, b1. Seems to be a pattern emerging here, but let's go and do some more calculations. Let's calculate now the second derivative. The second derivative will simply be, quite simple to calculate it. It's just going to be bk into k minus 1 into x minus c to the k minus 2. And of course, term by term, it would mean 2b2 plus 3 times 2 times b3 into x minus c plus. So it means that now f dash of c is going to be what? Let's have a look. Well, this term and all terms onwards will be 0. So that means we'll be left with 2b2. But that implies that b2 in fact is f dash of c divided by 2. Okay, so that's useful. Let's keep that there. Move on and calculate one more term, one more derivative, the third one. So the third derivative of the power series, again, now it's shouldn't be very difficult to calculate this. We have k minus 1 into k minus 2, x minus c to the k minus 3. And of course, term by term, it's just going to be 3 times 2 times b3, okay, plus the next term, I'm going to write it for you, is going to be 4 times 3 times 2 times b4 into x minus c. That's what's just going to into x minus c. Plus, we have the remaining terms. Calculate now f triple dash third derivative at c. We would end up with 3 times 2 times b3. Okay, and all the other terms would just disappear. So this would imply that, in fact, let me just change the color there, b3 is equal to the third derivative at c divided by 3 times 2. So let's look at these and try to see if we can figure out a pattern here. Okay. Well, what is noticeable is that, I can almost guess that the fourth derivative at c. Now, by the way, let's go back here and nothing more we can do about this, but here, if you notice, what is this actually? This is just the third derivative at c divided by 3 factorial. This can be written as the first derivative at c, second derivative at c divided by 2 factorial. Oh, by the way, I just noticed a mistake here. Sorry about this. Let me just correct those. These are second derivatives. Okay, sorry about that. Okay, so instead of calculating the fourth derivative at c, I'm going to go directly and say the following. It seems that b4 is going to be the fourth derivative at c divided by 4 factorial. And therefore, as I keep going down this route, the n plus 1th term, or the I should say nth derivative, okay, is going to be, so the n is going to be equal to the nth derivative, okay, at c divided by n factorial, and so on and on and on, as how we will get all these coefficients. So basically what it means is, what it boils down to, fx, any function, can be written as a Taylor series, which is an infinite series, of course, with the bk's as follows. The kth derivative at c over k factorial x minus c to the power k. And we call this is called the Taylor series of fx expanded about x equals c. Okay, so this is called this is the Taylor series expansion of f of x about x equals c. Right, so that basically is what the Taylor series is about. That's how we get that formula, and now we're going to look at some examples of how we calculate the Taylor series. So let's look at an example now of how we find the Taylor series of a function. So the example we're going to look at, excuse me, is fx equals e of x. In order to calculate the Taylor series, we proceed as follows. First of all, we calculate the first derivative. Now with each of these values, and we are going to calculate the Taylor series about x equals, say for instance, 0. This means that c is going to be 0 here. Okay, so it will say something like find the Taylor series of ex about x equals 0. Okay, that would mean that you're going to use c equal to 0. Do not substitute x equal to 0 in the expression. There will be no power series otherwise. Okay, so f dash is equal to ex. So f of x equals ex. This implies that f of 0 is equal to 1. F dash is ex, which implies f dash of 0, 1. Now you can see a pattern clearly emerging here. We know that all the derivatives of ex are simply ex. So therefore, we're just going to get a bunch of 1s. So if I go down here till the nth derivative, for the sake of argument, it's still going to be ex, and the nth derivative at 0 is still going to be 1. Okay, so now we're in a position to actually write down the series. Let's have a look at what is the Taylor series of ex. So we would say then that ex is equal to, term by term, if we were to go, it would be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial plus so on and so forth. Now we can write this in the summation notation as the full series. Since we have the kth term, we can write it as k equals 0 to infinity, and we have x to the k over k factorial. That's what seems to be the Taylor series of ex. Now the next question that arises should arise normally in your mind is, okay, so I've got a power series now. What do we usually do with the power series? Well, we check it for, we try to look for its radius of convergence. So let us do that. So here we'll use the ratio test as usual. So that means that limit as k goes to infinity of x to the k plus 1 over k plus 1 factorial. Of course, absolute value multiplied by k factorial over x to the k. Cancels with the factorial. Xk goes here. Leaves us with limit. K goes to infinity. X over k plus 1. Okay, so it gives us x over k plus 1, and as k goes to infinity, that goes to 0, which means that this implies convergent for all x, okay, i.e. for x belonging to minus infinity to plus infinity, infinite radius of convergence. So it is convergent everywhere, and that's a pretty strong result. So it converges absolutely for all x. Okay. Now I'm going to show you one other thing here that's quite important, and that is that in cases where we can actually write the kth term, it is possible to do it almost all the time. Sometimes it can be a little bit more challenging to write the nth term, but as in this case, it is possible that we could write this as a polynomial Pn of x, where we have k equals 0 to n instead of infinity, And the same thing. So you have x to the k divided by k factorial. Now this is known as, this is called the Taylor polynomial. Okay, it's called the Taylor polynomial of degree n. Okay, so it's an actual term. It's called Taylor polynomial. We'll be using this term later. As you know that in the topics that we're going to discuss, one of the topics is going to be estimating the error in a Taylor polynomial. So approximation. So this is a Taylor polynomial where all we've done is, if you notice that here, in this case, there you'll see there's infinity, and here we have n. So that's all you do. That's the only change you need to make, is to change the infinity to an n, and that's it, and you're good to go. So that's a Taylor polynomial. Okay, so I'm going to try to show you on a graph how the Taylor series in fact approximates a function. Now this particular case, as I said, is the Taylor series we just looked at, which is of ex around x equals 0. So first of all, x equals 0 would be this point here, okay, in blue. Okay, so that's the x equals 0 point. I'm going to put a big spot on that so that you can see that. Now we know that ex equals 0, if we start with the first term, is 1. Now if we just plot, here's in red what you see is ex. So what I'm going to do is I'm going to plot the first one, which is just in fact 1. So just the line 1 to show you. And there it is. So that's the line x equals 1. So that's when we have just 1 as our Taylor polynomial. Now when we look at 1 plus x, so we have plus x. So plus x would mean that we would have another line, but this time the line would be going through minus 1 and would be at x equals 0, it would be 1. So it will be this line, in fact. So let me just draw that here. So that would be that line. Okay. So now as you can see, the first line is very crude. The second line is also crude, but a little better. The next term that's coming, so plus x squared over 2 factorial. Now the x squared over 2 factorial, okay, would look, I'm going to approximately do this, so it'll be approximately this way. So it's quite close to this side, and then it goes through here quite well, and around just about over 0.5 it'll start to turn where it's, and then go up like that. So it's a quadratic, of course, 1 plus x squared over 2. So as you can see, it's getting closer. I mean, remember the red line is the original ex. Now if I were to take one more term, so let's say the next term is x cubed over 3 factorial, and 3 factorial would be 6. So we have an x cubed over 6. And this is very interesting. So I'm going to draw this for you approximately. And again, it's going to be on top of this, going quite well on top. Goes down here and over up to here, starts to separate, and goes through minus 1.5. So it goes down like that. So as you can see, it's a little bit closer. And if we do one more, which is the fourth order polynomial, let's go this time black. So the fourth one will be right on top of it, coming down, and this time it'll stay longer a little bit, but eventually would turn away again. So as you can see, it's starting to get closer and closer. And what I'm going to do is that, so that one is basically with the fourth term. So x4 over 4 factorial, which is 4 3 is 12, 2 is 24. So it's x4 over 24. Okay, and in this way, now I'm going to show you just very quickly what approximately the ninth order polynomial will do. okay, which is up to x9. So with x5 over 5 factorial plus up to, say, x9 over 9 factorial. If we go to the ninth, in fact, interestingly, I'm going to do this in black again. For this particular scale that we're looking at, it's almost exact. Okay, so I'm just trying to demonstrate, give you an idea so you can get a feel for what the Taylor series actually does. Remember, it's an approximation. So as you take more and more terms, the approximation becomes better. But one thing to keep in mind is that this point here, okay, this point is very important because this particular Taylor series is about c equals 0 or x equals 0 rather. Okay, so it's the more terms you take, it's very accurate close to this point. If you go further away from the point, then then the Taylor series becomes less and less. You'll have to take more and more terms to get it to be more and more accurate or closer to what it's trying to approximate. Okay, so hopefully that gives you some idea about how the Taylor series works. So the Taylor series about x equals 0 is also referred to as the MacLaurin series. Okay, so called the MacLaurin series. So just another thing to keep in mind, there's another series. It's very well known. The MacLaurin series is quite famous, quite well known. But it is specifically a Taylor series about x equals 0, expanded about x equals 0. Okay, so Taylor's theorem and the remainder. Basically, here's the statement of the theorem. So let's just go through it. It says that suppose so it says suppose that f has n plus 1 derivatives on the interval c minus r to c plus r for some r greater than 0. And r, of course, we are referring to here is the radius of convergence. Then for x belonging to this same interval c minus r to c plus r, where f has these n plus 1 derivatives, the function is approximated by this Taylor polynomial Pn of x. And the error in using Pn of x to approximate fx is Rn of x. This is the remainder here. So this thing we call that the remainder. And we've seen this before when we were studying infinite series. Okay, so this is the remainder term, and clearly it would be the difference between fx, what you're trying to approximate, and the difference between this and the approximation. So essentially that would give you this result. Now, where does this come from? If you look at this term, it looks very familiar. In fact, let me remind you with the Taylor series of f of x, the Taylor series or the Taylor polynomial. Let's say the Taylor polynomial better. So the Taylor polynomial is k equals 0 to n fk at the derivative at c divided by k factorial into x minus c to the power k. So that basically is the Taylor polynomial, the nth order Taylor polynomial. Now, what does this look like here? Now, if you notice, everything looks very familiar. This looks like the n plus 1th term here. And that's what it is, in fact. The only thing that looks a bit unfamiliar, perhaps, is this z. What is this z doing here? Well, let's look in more detail in part of the theorem, because the theorem states that this is true for some number z, okay, z between x and c. So z is some number between x and c. So it depends on, first of all, we need to know our c and we need to know our x, and it would be some number in between those two. So that would be the approximation of this z. Now, the reason we use the z here is simply because what you're looking at is remember, the n plus 1th derivative is supposed to be at x, and the only thing we calculate is the n plus 1th derivative at c. Now the Taylor polynomial is an nth order polynomial, so it stops at n. So this is the n plus 1th term, so essentially in a way we're saying that we're going beyond that. So when we go beyond that, that's why we use this arbitrary value z, but it's in the neighborhood of x and c, so it's in between those two. Okay, right. So as a quick example of this, if we go to the Taylor series of EX, which we have actually calculated, so the Taylor polynomial of the Taylor series of EX is this one. Okay, let me just write it down here again quickly to remind you. K equals 0 to infinity. Okay, and it's 1 over k factorial times x to the k. Okay, so that's the Taylor series. Now this is an infinite series. Now, if I were to look at the remainder term, so Rn of x in this case would be clearly the n plus 1th derivative. Okay, so it would be, I'm just going to write it again for you. So n plus 1th at z divided by n plus 1 factorial at x minus 0, of course. So it's just going to be x to the n plus 1. Okay, because c is 0. Now, if you look at this, we know, for instance, that that's going to end up becoming e to the z, okay, over n plus 1 factorial, okay, no big deal there, into x to the n plus 1, okay. So that's fair enough. Now, what is this z? Well, of course, z would be something between, remember, it's between x and c. Okay, this z is something we need to get a little handle on. So in order to understand that, keep in mind that when there are two possibilities. If x is greater than 0, under that condition, then z would be something that is positive, so therefore it would be between 0 and x in this manner. Okay, it would be like this. And that would clearly mean that e of z would be less than e of x, because as x increases, z goes up. So clearly, in this particular case, for x positive, ez would be less than ex. On the other hand, the other possibility is if x is less than or equal to 0. Then it's very simple to see that z would be something then that is greater than or equal to x and less than or equal to 0. Okay, that's quite straightforward to see. Okay, which would mean that this would be the opposite would now be happening, and ez, okay, would now be less than or equal to e0. Because what I'm going to do is I'm going to take the largest possible value. So ez would clearly be bounded above by e to the 0, which is 1 in fact. Okay, so ez would be bounded above by 1. So if we define some number, say m, which is the maximum of these two, ex and 1, for the sake of argument. So it's the maximum value between either ex or 1, whatever x might be. Then for any x, any n, we have that clearly ez would be bounded above by m, because it's the largest value that we're choosing. Look, I mean, m is a number that's the maximum of ex or 1, whichever is the larger of the two. And clearly ez would be bounded by that. Ez would be less than that, okay? That's clear. Is we now have a bound for our remainder. So our Rn of x, the size of Rn of x, is going to be what we have there, which is this expression that I just showed you a second ago, ez over n plus 1 factorial into x to the n plus 1 power, okay, and of course the absolute value of that, okay, absolute value of x, which is going to be less than or equal to, now ez is bounded above by m, so we're going to replace it by m because we don't know what z is. So remember, the reason for doing all of this is simply so that we can get an idea or a handle on this ez. Okay, and here we have the absolute value to the power n plus 1. So it's bounded above by that, and we know the remainder is now therefore bounded. So as n goes to infinity, if we were to explore this further, as n goes to infinity, we've already shown that actually the series is convergent everywhere. So anyway, I just wanted to show you that very quickly as a bound. The next thing we're going to do is we're going to see how do we practically use the remainder. This is not a real practical application that I'm so interested in. It's a nice mathematical exercise to see bounds and to show convergence of a series, but of a particular Taylor series. But what I'm really interested in is where do we practically use a Taylor series? Well, we practically use Taylor series usually for calculating transcendental functions like log, exponential, sine, cosine, tan, all the trigonometrics. So that's where the Taylor series really becomes a very useful tool. So what I want to do is I want to see, okay, here's a very interesting question. So fair enough, I'm saying that let's say an example. I'm going to calculate the first. I'm going to calculate the Taylor series of f of x as another example, or ln x. Okay, I want to calculate that. So fx is equal to ln x, which and I'm going to calculate the Taylor series about the point 1, x equals 1, because we've already done x equals 0, which is a MacLaurin series. So this is our objective. We want to find the Taylor series. I'm going to call it TS, Taylor series, about the point x equals 1. So that's what we are planning to do now, and then I'll explain to you how the Taylor theorem, where the remainder theorems can be very useful in calculating terms and so on and so forth. So let's just do that first of all. So the first thing we have is we calculate, so fx is equal to ln x, which implies that f of 1, okay, is ln of 1, which is equal to 0. Okay, ln of 1 is 0. The next thing we do, of course, calculate the first derivative. So the first derivative of ln x is 1 over x, which implies that f of 1, okay, is equal to 1. Okay, f double dash, second derivative, is minus 1 over x squared, which implies that f dash of 1 is minus 1. Next term. We'll need a few terms so that, because we will need the nth term here, so we need to look at a few terms in this particular case. So this one now is going to be 2, and I'm going to start writing these in negative powers rather than over a cube, which implies this will mean that this, sorry, that's second derivative here, and that's the first derivative here. Sorry about that. So the third derivative at 1 is in fact 2. Okay, it's equal to 2. Next one is the fourth derivative, and we need to keep going till we can actually see a pattern emerging. So I'm going to write that down as minus 3 times 2 times x to the minus 4. Okay, so this implies that the fourth derivative at 1 is minus 3 times 2 times 1, for instance. And I'm going to put that in a bracket and leave the negative sign outside. So I'm starting to see a pattern emerge here. I would guess that here the kth derivative at x is going to be, in fact, minus 1 to the k plus 1, okay, into k minus 1, because it's 1 less factorial. Okay, I'll explain that in a second. X to the minus k. So let me just calculate this, and then I'll explain, if you don't understand, how I get that. Okay, so here the kth derivative at 1 is going to be minus 1 to the k plus 1, all right, into k minus 1 factorial. Okay, now let me explain how this works and why this comes about. So here's a very simple way, because you can almost, well, clearly we are seeing that except for the first term, which is 0, we have a positive 1, we have negative 1, we have 2, then negative. So what we see is the sign keeps changing, right? And for the first derivative, it's positive. So here, that's why I've used the k plus 1, because when 1 plus 1 is 2, squared gives us plus 1. Now let's have a look at these numbers. So the sign is taken care of. Let's look at the numbers. So we get 1, then we get minus 1, okay? Then we get 2. Right, so when it's 3, I get 2. When it's 4, fourth derivative, I get 3 factorial. So 2 is the same as 2 factorial, 1 is the same as 1 factorial, and 1 here is the same as 0 factorial. So let me just make a note of that. So okay, so I want that to be positive, so that's going to be minus 1 squared. So it's positive and it's 0 factorial. That's the same as minus 1 cubed, and this would be 1 factorial. That's the same as minus 1 to the 4 gives me a positive number into 2 factorial. That's the same as minus 1 to the 5 gives me a negative sign into 3 factorial, and so on. Now notice here that that's 2 factorial and that's the third derivative. Okay, 2 factorial, third derivative, fourth derivative, 3 factorial, so 1 less. So that's why you have k minus 1 factorial, and the power is k plus 1 because we want the first, this one here, to be positive instead of negative. Okay, so that gives us the term, the kth derivative. Okay, let's move on. So far everything looks pretty straightforward. Let's write down the Taylor series of this ln x. So the Taylor series, it's going to be the k equals 0 to infinity. Okay, fk at 1 divided by k factorial into x minus 1 to the k. That's what it is, and what it will become is, let's look at a few terms just for the sake of completeness. So it's going to be x minus 1, okay, minus a half into x minus 1 squared, okay, plus 2 over 3 factorial into x minus 1 cubed, okay, plus dot 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 minus 1 to the k plus 1, okay, k minus 1 factorial over k factorial, okay, into x minus 1 to the k, plus, it's an infinite series, so it goes on then afterwards. Okay, so that looks like we can actually write it down, simplify it a little bit, clean up, and because we have the kth derivative, so actually we can write it like this. Now what you'll notice is that the 2 cancels with the 3 factorial, the 2 of the inside the 3 factorial, so what it looks like, well, okay, let's just go to the kth term, k minus 1 factorial over k factorial. Okay, let me put a little circle around that, and what does that mean? So that's like k minus 1 factorial divided by k into k minus 1 factorial, right? So that clearly cancels, leaves us with a 1 over k. So that means that we end up with our negative sign, which is k plus 1, divided by just k, no more factorial, into x minus 1 to the power k. So that's our Taylor series. That's our Taylor series for ln x. Okay, so next question we have is, we have a power series. So now what we need to do is to prove that this power series, what is the radius of convergence of this power series? So let's continue with that. So we'll start with, well, let's write this in summation format. Okay, k equals 1 to infinity. And of course here we have now our kth term, k plus 1 over k into x minus 1 to the power k. Now we're in a position to start looking at the ratio test. So in order to find the radius of convergence, as we usually do, limit k goes to infinity, k plus 1th term. Now remember that ratio test requires the absolute value. Therefore, there is no need to take the minus 1 to the k plus 1. So all we have here is this k plus 1 over k plus 1 multiplied by the reciprocal of the kth term. So that's going to be this and that. Okay, this cancels with the k plus 1 power. This gives us limit k goes to infinity, x minus 1 into k over k plus 1. Now, you all know that the x minus 1 can be taken out. Okay, and it's a good idea to take it out because then you can clearly see where how to calculate your limit. So k over k plus 1 goes to 1. So this is equal to x minus 1. Okay, because this limit here is going to 1. Okay, so we end up with just x minus 1. Now the ratio test tells us that x minus 1 less than 1, we have convergence. Okay, so if that's the case, then this implies that x minus 1 is greater than minus 1 and less than 1, which further implies that x is greater than 0. Add 1 to all sides of the inequality, less than 2. So this is where we know it is convergent. Okay, we know it's convergent here. Now, we also know that for x minus 1 greater than 1, which implies the fact that x is either less than 0 and x is greater than 2, we have divergence. So it's divergent as long as x is less than 0 or greater than 2. And that leaves us with the last situation, which is when x minus 1 is equal to 1, and this implies that either the situations of x equals 0 and x equals 2. Now the problem here is these have to be done individually, and what I mean by that is you have to substitute. Let's take x equals 0 first. So if we take x equals 0, our power series becomes k equals 1 to infinity minus 1 to the k plus 1. Put the 0 in there, you get multiplied by minus 1 to the k. And all of this is divided by k, of course. Now that, as you can see, is really just k equals 1 to infinity minus 1 to the 2k plus 1 divided by k. And you can tell easily an odd power, that means always odd powers, to minus 1 will lead to a consistent minus 1 over k. Now that is really the negative harmonic series. That's just a harmonic series with a negative sign, so that is divergent. Therefore, divergent. So x equals 0 gives us a divergent series. So that means the last thing we need to then check is for x equals 2. We substitute that in, and the power series that comes out is minus 1 to the k plus 1 into 1 to the k. Okay, and so I'm going to write that for you just so you can see it. 1 to the k. 1 to the k is just 1 over k. So this results in k equals 1 to infinity. Okay, minus 1 to the k plus 1 over k. Now that is the alternating harmonic series. Alternating harmonic series, conditionally convergent. Okay, so we will note that it is conditionally convergent between 0 and between 0 and 2. So we have a half interval of convergence for conditional convergence. Otherwise, between 0 and 2, it's absolutely convergent. So you need to be a little careful. It's a little bit of a subtlety, and so just be aware of it. Okay, so now here's how we can use this. I'll just summarize that again. Log x that's the Taylor series log x. That means Taylor series TS. Taylor series about x equals 1. And we know the radius of convergence x between 0 and 2. So it has a limited radius of convergence, and we need to be careful about that. Now here, where can we actually use this? Let's say, for instance, if we wanted to calculate the log ln of 1.1. So we're interested in calculating ln of 1.1. Now, in order to do that, we could. This is not a big deal. X is going to be 1.1, so that means that in our series, we'll just replace x with 1.1 first of all. Okay, and that would mean that we could easily approximate that. But here's the problem. Now, this is an infinite series. An infinite series, in theory, is infinite. So you cannot, it doesn't stop. That's precisely where we use the Taylor polynomial. So we could, for instance, say here, okay, we're going to use the Taylor polynomial, okay, as follows. K equals minus 1 k plus 1, and it's going to be 1.1 minus 1. 1.1 minus 1 is 0.1 to the power k. And all of this is divided by k. So that is ln of 1.1. But here's another question. Fair enough. You change the infinity to the n, but I don't know what n is. How many terms is sufficient? That is the key question. So that depends on the user. Now the user may come back to you and say, well, look, I want an accuracy of 1 into 10 to the minus 10, for the sake of argument. Somebody says, I want an accuracy of 1 into 10 to the minus 10. So I want to use the remainder theorem to help me to calculate, or provide the how many terms to find an n that gives me the accuracy of desired accuracy of 10 to the minus 10. So this is how I'm going to do that. This is a practical example of the remainder. So now, first of all, let me show you what is Rn of 1.1. Okay, for this particular series. So I need to calculate that first of all. So in order to do that, here I'm going to go to the definition, which is the n plus 1th derivative at z. Okay, alrighty. And we have n plus 1 factorial down here. Okay, and we have over here 0.1 to the n plus 1. Okay, so that is what we're trying to estimate. Okay, so what we can simplify that, of course, because we know the n plus 1th term. We will not use the negative sign anymore. The minus 1 to the k plus 1 is irrelevant because we're taking absolute values. So that's equal to... So in order to calculate this, let me quickly remind you that we had calculated earlier that the kth derivative, okay, of ln x turns out to be equal to minus 1 to the k plus 1. Okay, then we had the k minus 1 factorial. Okay, you can go back in the video and check that. But here's a quick reminder, and x to the minus k. That's what we end up with, in fact. So here it's z. So basically what that means is we're going to have the minus 1 to the k plus 1 disappears. I end up with minus n minus 1. Okay, that's what that becomes. It's minus n minus 1. I hope that's reasonably clear. Minus n minus 1. So n factorial divided by n plus 1 factorial. Alright, and we then of course have the 0.1 to the n plus 1, and we're taking the absolute value of all of that. Okay, slowly, let's move slowly now. Can we simplify that further? Yes, we can, of course. We can write that as, well, that's 0.1 to the n plus 1 is going to be positive always, so let's leave that. And it's divided by n plus 1, okay, because the n factorial will cancel with the n plus 1, n factorial down below. And here, let's write this as z to the n plus 1. Okay, we're going to write this as z to the n plus 1 because we're going to bring z to the minus n minus 1 below. Now remember, z is here, z is between, remember, its definition, by definition, it's between x and c. X is 1.1 and c is 1. So it is a number, it is somewhere between 1 and 1.1. Okay, so z is something between 1 and 1.1. Now z is in the denominator. So if I write this down, I hope it will be clear that I can actually replace this z by 1, in fact, because I want to put the smallest value here. Okay, that will make this the largest. Because 1 will be bigger. So this is going to give me 0.1 to the n plus 1. Yeah, 0.1 to the n plus 1 over n plus 1. Much simpler now to see. Okay, so that is my term. Now what do I want? I'm saying that I want the remainder term 1.1. Okay, we're saying that is bounded above by this term 0.1 to the n plus 1 over n plus 1. And that, of course, we want that to be bounded with an error of, because this is the remainder. So we want the remainder to be, say, 10 to the minus 10. Now if we do that, okay, we find that now here a lot of students get a little confused about solving this particular inequality. So you start looking at logs and so many different things, and what you don't realize is that actually it's a very easy way to do this. I mean, this is 10 to the minus 10. You have 0.1 to the power n plus 1. The easy guess here would be, and remember 0.1 is 1 into 10 to the minus 1. Okay, 1 into 10 to the minus 1. So what you're looking at is 1 into 10 to the minus 1 to the power n plus 1 divided by n plus 1. So think about it. If I let n, if I let n be 9, I'm going to get 1 into 10 to the minus 10. So if n were 9, then I would get 1 into 10 to the minus 9, or minus 10, sorry, because it's 1 plus 1, divided by 10, which is 1 into 10 to the minus 11, which is smaller than 1 into 10 to the minus 10. So that's the smallest, that's the first value of n that will actually make it just less than 1 into 10 to the minus. So that tells me that 9 terms in the series would be sufficient to get me the accuracy I desire. So if we go and calculate, in fact, log of ln of 1.1, okay, it's going to be, in fact, I'm going to take 9 terms. So that means we're going to go and take 0.1 is going to be our first term. Okay, 0.1 minus a half, 0.1 squared, plus 1/3, 0.1 cubed, minus a quarter, 0.1 to the 4, plus 1/5, 0.1 to the 5, minus 1/6, 0.1 to the 6, plus 1/7, 0.1 to the 7, minus 1/8, 0.1 to the 8, and plus 1/9, 0.1 to the 9. Now, if you were to do this, okay, it turns out that that's approximately turns out to be 0. So you can see the accuracy. You have to trust me that these calculations are correct. It's quite a lot of calculation to do, but anyway, that's to the 10 to the minus 10 accuracy as desired. So this is a very nice application of the remainder theorem. So here's a nice trick. This is the Taylor series about x equals 0 that we've already looked at of e to the x, or say e to the t. Now you can use the same one to, say, for instance, calculate the e to the exponential, or the Taylor series of e to the 2x about x equals 0 by simply replacing, this is k, sorry, by simply replacing, okay, t with 2x. So it's 2x to the k. All right, which means this becomes 0 to infinity, 2 to the k over k factorial into x to the k. Right? So that becomes your Taylor series. Now you can just replace the t in there to see it term by term. Similar way, you can do e to the x squared. So that would mean k equals 0 to infinity, 1 over k factorial, x squared, okay, replaces the t and goes up here. So we can simplify that a little bit and write it more like this, which is x to the 2k. So it's x to the 2k over k factorial. Now these happen to be convergent everywhere, just like the first one. One last thing I want to do before we leave, before we finish Taylor's series, is an application of Taylor series. As I've mentioned already, calculators use, how do you think your calculator calculates sine x? Okay, so here's the MacLaurin series of sine x, okay, is basically sine x is x minus x cubed over 3 factorial plus x5 over 5 factorial minus x7 over 7 factorial plus dot dot dot. Okay, that's the Taylor series of sine x, which you can write in this form as well, 0 to infinity. Okay, so that's the kth term. K equals 0 to infinity minus 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. That's sine x. Now your calculator, like a 10-digit accuracy calculator, using the remainder theorem, we can see how many terms in the series in the Taylor polynomial would be sufficient to get 1 to the minus 10, for instance, 10 decimal place accuracy, and so on and so forth. Now, of course, you can calculate the MacLaurin series, you can calculate the Taylor series. As you move away, I mean, you can get more and more accurate by calculating. For instance, if you wanted to calculate sine of in radians, suppose you wanted to calculate sine of 5 radians. So if you wanted to go to 5 radians, the best thing to do, either use periodicity, or you could simply, map it back to, between 0 and pi, between minus pi and pi. Or what you could do essentially is even move it, take your Taylor series about 5, for instance, or about 4, as close as possible to the target value. And then you use the remainder theorem to calculate the number of terms. Now, one other application is you've noticed that one of the things we've been doing in Calculus 2 is looking at integration. And one thing we have definitely realized is that integration is not necessarily a trivial exercise. It is, and I've showed you that this integral, e to the x squared dx, is something that doesn't have an antiderivative. One way to approximate it is basically to replace it by its Taylor series approximation. Basically, it boils down to just let's take a few terms here, plus x squared plus x4 over 2 factorial plus x6 over 3 factorial plus so on and so forth. And of course, with respect to x, we know term by term integration can be done very easily. Well, there's nothing difficult here. Actually, it's quite straightforward. The integral of 1 is x plus we have x cubed over 3 plus x5 over 5 times 2 is 10 plus x7 over 7 into 3 factorial. So that's 42. Sorry, that's 42. And so on and so forth. So you see, we can actually calculate the integral. But the only problem is it'll always be an approximation, because this is an infinite series, what you see here. But in any case, it is a way out. It is a way to calculate the integral, in other words, to approximate it. So that brings us to the end of this section on Taylor series. We've covered the Taylor series, the MacLaurin series, the remainder of the Taylor series, and of course, we just looked at a few applications as well. Okay, thank you.